Bismillahirrahmanirrahim. In this video, we are going to go through example 8-9, which is on DC generator, and this is part of lesson 4. Let me first read out the question. A separately excited DC generator is rated at 172 kilowatts, 430 volts, 400 amps, and 1800 RPMs. It is shown in the figure above. You can see the equivalent circuit, and its magnetization curve is as shown in the plot. We will see the plot later. This machine has the following characteristics: armature current equals to armature resistance equal to 0.05 ohms, RF or the field resistance is 220 ohms, adjustable R is 0 to 300 ohms, and remember this adjustable R is in series with RF. And then VF or the field voltage is equal to 430 volt, and the number of the turns in the field winding is 1000 turns per pole. Question A: if the variable resistor adjustable R in this generator's field circuit is adjusted to 63 ohms and the generator's prime mover is driving it at 1600 RPM, what is this generator's no load terminal voltage? Okay, to answer this question, what we are going to use is the fact that the speed is directly proportional to the internal generated voltage EA. So again, the machine speed is directly proportional to the internal generated voltage EA, which means that if the speed is doubled, then the internal generated voltage is doubled. If the speed is tripled, the internal generated voltage will be tripled as well, and so on. And another thing that we need to understand, and we have otherwise we will not be able to solve the problem, is that when it says there is no load, it means that the line current IL is equal to 0. Again, when it says that there is no load, when the generator doesn't have any load, it means that the line current IL is equal to 0. And where is IL? IL is the current that flows through the terminals. This one here. Okay. Right. And then for this particular type of generator, IL will be equal to IA. So these two lines, these two currents, the line current and the armature currents, are of the same value. Okay, now to solve the problem, as I said before, that we are going to use the fact that the speed is directly proportional to the internal generated voltage. So the speed is proportional to internal generated voltage, meaning that if you have two speeds, this will be equals to the ratio of the internal generated voltage as well. Okay. Okay, the notation 0 is used for the rated condition. So N0, for example, is the rated speed, and EA0 is the internal generated voltage when the generator is running at its rated speed. And the rated speed for this generator is 1800 RPM. So which means that this curve that we have here, this is true for the speed of 1800 RPMs. Okay, so it means that we know this value already. This is 1800 RPM, yeah. And then what is the EA0, the internal generated voltage at this rated speed? We can use the magnetization curve, yeah. But to use the magnetization curve, we need first to find what is the value of the field current IF, and then we can work it out by doing these steps here. First, we work out the total field resistance, and then we can work out the field current by dividing the field voltage by the field resistance, yeah. Because you can see this is IF is here, yeah, IF flowing here, and this is simply equals to this IF is simply equals to VF divided by the total resistance, yeah. Okay, so you've got the IF is equal to 5.2. Then you can then use the magnetization curve, yeah. Okay, then you can check IF is equal to 5.2, which is this is 5.2. So if you use this point and then project it to the curve, you get this, yeah. And then you project it to the y-axis, then you get a value for the internal generated voltage of 430 volts, yeah. This value here, in case it's not very clear, so that's the value 430 volts. Okay, so this will be our EA0, yeah. The EA value when we use the magnetization curve of this machine. Okay, so this is again what was it before, 430 volt, yeah. So this is equals to 430 volt. Okay, so you've got the this two variable values, and then the question is, what is the value of the no load voltage when the speed is 1600 RPM, 1600. So when the speed is 1600, we can then work out the value of EA, yeah, which is EA will be equal to 1600 divided by 1800 times 430 volt, yeah. And what is the answer? We can just check the answer given by the book, which is 332 volt. This is the internal generated voltage. So if the question is not the internal generated voltage, so if you stop here, then your answer is not right, yeah, because you actually haven't answered the question, yeah. If you check, the question is what is the no load terminal voltage, yeah, no load terminal voltage. So the question is asking what is the value of VT, not EA, yeah, VT when there is no load. Now again, as I said before, no load, yeah, no load means IL equals to 0, yeah, which means IA also equals to is equal to 0 as well. Then you can work out the value, then you, from there, if you use the KVL, yeah, from the equivalent circuit, EA is equal to VT plus IA RA. Yeah. Question B, what will its voltage be if a 360 amp load were connected to its terminals? Assume that the generator has compensating windings. Okay, 360 amp load, yeah. This is actually will be equal to IL. So IL, the line current, is 360 amps. Yeah? IL is 360 amp, and therefore IA, which is equal to IL, will be equal to 360 amp as well. Yeah? And then we just use KVL, yeah, this equation here, while IA is 360. Yeah. Okay, so that's done. So you should get 364 volt for the terminal voltage. Okay, question part C is the same as question B. However, now we've got armature reaction. Question B, in question B, we assume that there was no armature reaction. Okay, to answer this question, we can either follow the way it's answered here in the what's given in the textbook, yeah, that by using the effective field current. We can also look at it from the MMF point of view. So the total MMF, yeah, equals to the MMF generated by the field current minus the MMF generated by the armature reaction. Yeah. Okay, and then we also know that MMF is equals to number of turns times the current, yeah, that generates the field, yeah, or the induces the field. Okay, and then the total MMF in the system is equals to the number of turns, assuming that this is the generated by the effective current that goes through the field winding, yeah. So it's the number of turns in the field winding, yeah, times the effective current. Yeah, you can assume here that these two MMFs are in the opposite direction. Yeah. If you remember that the armature reactions weakens the magnetic field, i.e., if for example the main MMF is going to the right, yeah, then the one that is generated by the armature reaction will be in the opposite direction. I mean, this is a simplification, but more or less this is what's happening. So, which means that the total MMF, yeah, the total MMF will be the difference between the two, yeah, which will give us this. Okay, and yes, and this total MMF, if we assume that is generated by an effective current that goes through the field, then it will be equal to this, yeah? While the MMF due to the field current itself, the actual field current equals to NF into IF, and this is we don't need to change or substitute, because the value of the MMF due to the armature reaction already given in the question, which is 450 ampere turns, yeah? So this is equals to 450. Okay, and then if we divide all this by the field current, you will get IF, the effective field current, equals to IF minus 450 divided by sorry, not divided by an IF, but it's divided by NF, yeah? So this is divided by NF, and therefore the effective field current is 5.2 minus 450 divided by 1000, which is equals to 4.75 amps, yeah? Okay, so again, the actual field current is actually 5.2 amps, but because of the presence of this armature current, as if there is only a field current of 4.75 amps rather than 5.2 amps, and because as if there is only this amount of current, so the total magnetic field, yeah, in the system is also reduced, yeah? Okay, and now when we use the magnetization curve, this is the value of field current that we use. Okay, right, now again, just like before, we are repeating the same steps now, yeah? Just like when we answered question B, yeah? So we will use the fact that the EA is directly proportional to the speed, yeah? And then we've got all this value, yeah? N is again, we know already, 1600, and 0 is the base or the rated speed, yeah, is 1800 RPM, right? And then what about the EA0? EA0 is we should then for this one we check the magnetization curve, yeah? But now for the new field current, which is 4.75 amps. So if you use the magnetization curve, 4.75 is this point here, okay? And then you just follow this line, the dashed line. Well, in reality you will not have this line. You need to draw the line by yourself until it intersects with the curve. Then from the intersection point with the curve, then you project it to the y-axis, and then you should get the value, yeah? And again, in reality you might not have the value written, yeah? So you need to calculate or approximate what is the value for the internal generated voltage for that projected point, okay? Okay, in this case what we got is 410 volt, yeah, for EA, and therefore this is what we are using 410 volt for this EA. So EA0, the base rated voltage, so this is equal to 410. Okay, and then therefore you've got all the three values. You've got only one unknown, which is EA, so you should be able to work out the value of EA, right? And then you should be able to find that EA is equals to 364 volt for that speed of 1600 RPM. Now in the final final step is to find the terminal voltage. Yeah? Okay, and something to watch out, that the terminal voltage in this case is not equal to EA. Yeah? VT is not equal to EA anymore, because now we've got some load. We've got the IL and IA are no longer equal to 0. Yeah? So we need to use the KVL. Okay, so we use the KVL equation that VT is equal to EA minus IARA. Yeah, and then yeah, we've got all the values now. Yeah, we know the value of EA and this, so we just substitute these variables with their values, their corresponding values, and you should get the answer that VT is equal to 346 volts. Yeah, which is lower than before, and this is caused by, oh sorry, this is 346, which is lower than before. If you compare, so the output voltage of the generator was 364 volt before the armature reaction, but once we got the armature reaction kick in. Next question, part D. What adjustment could be made to the generator to restore its terminal voltage to the value found in part A? So this is an example of the applications of voltage control of the generator. So we notice that when the load changes, when the load changes, then the output voltage was affected. Yeah? In this case, the output voltage was lower. Okay, so what can we do to adjust so that the terminal voltage become equal to the original value that we found in question A? Yeah. So if you check, the value was 382 volt, 382 volt. But when we had the load and the armature resistance reactance as well, the voltage dropped to 346 volt. So what can we do to adjust? Okay, the answer is given here. The voltage at the terminals of the generator has fallen. Yeah. So to restore to its original value, the voltage of the generator must be increased. Okay, so we need to increase VT. And how do we increase VT? VT is equal to EA minus IARA. So one way of increasing VT, if you want to increase VT, then we need to increase EA. Okay, there's another way, but this is the one of the ways. So to increase VT, we need to increase EA. And how do you increase EA? If you check the magnetization curve, if you go to the magnetization curve, to increase VT, to increase EA, then it means we have to go in this direction. It means that we need to increase the field current as well. Okay, and then how do we increase the field current? We increase the field current by using a lower value for the adjustable R, because IF field current equals to VF over RF plus. So again, if you want to increase IF, then we need to reduce this, because these two values are fixed, VF and RF are fixed, so what we can do is we reduce the adjustable R. Okay, so that's part D, and then part E is the calculation. Yeah. So what is the new value of adjustable R that we need to use? Yeah. So that the output voltage becomes the same as it was before. Okay. Okay, I think you can follow the steps by yourself. There's nothing tricky in here, and most of the steps have been